Well, ladies and gentlemen, thanks very much for joining us for the second of our special PechaKucha events as part of Explorathon 2021. Explorathon is part of European Researchers' Night. So I'm Chris Crowley, I'm Public Engagement with Research Manager at the University of Aberdeen. And in the University of Aberdeen, we take care of Explorathon, which is what we call European Researchers' Night in Scotland, where we deliver a pan-Scotland series of public engagement events. And as I say, it's part of European Researchers' Night, which is funded by the European Commission and is the largest public engagement with research event in Europe. And tonight, we're on the second of our PechaKuchas, and I'm sure many of you are familiar with PechaKucha as a talk format, but for those of you who aren't, I'll just do a very brief background. It's from a Japanese expression. It means chit-chat. It encourages people to be informal and entertaining, but also focused in their presentation because they have 20 images, no more, no less, and 20 seconds for each image. And after the 20 seconds, the slide moves on automatically. So they have a total of 6 minutes and 40 seconds. So it's a brief talk. And we've got quite a few talks tonight covering various aspects of engineering and technology research across Scotland. So we'll meet the researchers and hear about their latest research. That's enough from me. We should move on, first of all, to Dr. Milan Markovic, who is a research fellow at the University of Aberdeen. And Dr. Markovic starts with the very interesting topic of AI is watching, but who is watching AI? So, Dr. Markovic, over to you.
Artificial intelligence, or simply AI, is a mainstream term often used and also sometimes misused by many people today. Some say that AI will take all our jobs and maybe even kill us, and others say that AI will help us cure all the disease and make our lives easier and safer. So what's this hype around AI really about? Recently, real-world AI applications are becoming an exciting reality, and they are driving innovations in automation which have rapid disruptive effects on industries and also our personal lives. AI does learn in its limited way quite a lot about us as well. It can, for example, recognize our faces, gender, and age. AI is also getting better at predicting our behavior. It knows what we will buy, what video we would want to watch next, and even who we might like to go on a date with. But AI has no morals. It can only do what humans build it to do. AI will happily assist you to catch criminals, as well as to spy on your employees, and recent experiences with real-world AI systems have shown us that it is very easy to make mistakes that result in biased, unethical, or even outright malicious AI systems. And we need to think carefully how we deal with these potential malicious side effects of AI, because the more we let such AI systems integrate into the very fabric of our society, the more difficult it will be to fix them later. This issue becomes even more important when we consider AI systems that will be much closer to us in the physical world. While there is a great potential for these systems to make our lives easier and safer in future, it would be also easier for such systems to cause real physical harm if something goes wrong. And we are not talking about the burnt toast here. AI can be biased, not necessarily through a fault of its own, but because it learns from biased data through which it observes the world. So for example, when the almighty Amazon designed an AI solution for screening job applicants, the AI model learned to discriminate based on gender because of a gender bias contained within the historical recruitment data that were used to train this model. This forces us to think and ask more questions, especially when it comes to general purpose AI systems, which are already being rolled out today, such as automated tumor detection for breast screening exams, to address a shortage of radiologists in hospitals. But how can we be sure that such AI systems are not biased against women from minority ethnic backgrounds? Or when we finally give up control of our cars and hand it over to the AI driver and we end up in a crash, how will we know what went wrong and, more importantly, who is accountable for the damages or even potential loss of lives? As it turns out, AI accountability is not very easy or straightforward to figure out. The law in most countries plays a fast-paced catch-up game with new evolving AI applications which are inevitably gaining more agency and autonomy. Lawyers and legislators are busy trying to tie in the new high-tech concepts within the traditional law context to enable AI systems to be held accountable. But to hold AI systems accountable, many questions need to be answered with acceptable evidence before we can even start pointing fingers. And when it comes to complex AI systems, the coexistence of multiple hardware parts and environmental factors make it very difficult to pinpoint the cause of an incident. AI models that represent the logic which makes decisions can be very complex mathematical representation of a particular domain. And sometimes, for example, as is often the case with deep neural networks, it is difficult to understand and explain why the AI system made some decision. And we also must ask what should happen when we prove that the AI system did something wrong. Obviously, it doesn't make sense to put your Tesla car behind bars if it caused an accident. Also, the car wouldn't probably be ordered to pay the fine for running a red light. So who do we actually hold accountable for AI's wrongdoings? The best answer we have for now, which also works with our traditional law systems, is that we need to find a human or group of humans that can be held accountable. But AI systems are complex and many people participate in their development and operation. And we can't just blame them all. People often assume that the fault in an AI system must always lead back to the programmer, but this is not necessarily true. Damage can be also caused because of a bad design, based on inaccurate understanding of the application domain, the AI system being deployed in a wrong context, or simply it not being used correctly by the end user. One useful analogy we can use here is the one of the lighted cigarette that burned down the house. While there were other factors contributing to the fire, like the presence of oxygen, only the person who lighted the cigarette could have done things differently and prevented the disaster, and as a result is accountable for destroying the house. But to be able to determine the cause, in other words, the lighted cigarette, we need to record a lot of information about the design, implementation, deployment, and operation of AI systems. And most importantly, we need to include important information about events that help us to identify the cause of an incident and which can be linked to humans. However, it is still a wild west out there, and recording such information has not yet been standardized, which makes it more difficult to audit AI systems. And in many cases, such information doesn't even exist, as its recording creates additional overheads that companies are not prepared to meet if they don't have to. At the University of Aberdeen, we are researching novel approaches to define important concepts that should be included in such records, and novel technologies that enable the capture of such information as interconnected knowledge graphs, so it can be easily navigated and understood by both humans and computers. But there is still a long way before complete solutions can be realized. It is important not to get carried away by the potential technological miracles promised by AI, which are often used as an excuse for limited accountability. And we need to continue with our efforts to maintain our control over such systems from legal and also technical, ethical standpoints.
Well, thank you very much. Fascinating, and indeed, it's something it's with us in our everyday lives. AI. I certainly have various devices which I know are probably watching constantly. Some of which I know are, some of which maybe I don't know. Anyway, moving on, because we do have an awful lot of speakers tonight. Is Marlene Cramer, who works at Napier University, and she's working on a Horizon 2020 funded project, and that project is called In Future Woods. And her presentation title tonight is, intriguingly, It's Good Enough, I guess. So, Marlene, over to you.
The other day I wanted to buy some wood planks to build a deck. So I went to a timber merchant, I gave them my budget, and I asked them to deliver to me whatever they could do for the money I had. 2 months later, they delivered this.
Well, apparently timber prices have risen to unprecedented levels in the last year. I am a wood scientist, and one of the sentences I probably read most is, "Wood is cheap and plentiful, so how come I cannot afford it?" Well, we are not the ones to control the prices. That's the Russians. And the Europeans. You see, the UK imports most of its structural timber from them. Why don't you sell me some nice UK timber then? I don't have any. I guess some important building projects bought it all? Nope, they burned it. They what? Yeah, they burned it for biomass energy production. Of course, not all of it, but more than 80% of homegrown hardwood timber, and half of the softwood timber is used for energy, chipped for panel products, pulped, or used in packaging and fencing. But why? Homegrown timber is not very well liked. People think that it's low quality compared to European timber. But the local timber has been used in buildings for hundreds of years. Clearly someone thought it was good enough. But back then people used to use it without thinking much about it. Nowadays you need to actually know that the timber you are using in construction is strong enough for the job. Unfortunately, we don't know much about homegrown timber. You are telling me that we can build spaceports in Scotland, but we don't know whether our wood is strong enough to build houses? Can't we do some research? Yeah, well, it's not that easy. Wood is a natural material, and its properties can vary a lot between trees, but even within a tree. And the properties also depend on forestry practices, on soil and climate conditions, and so on. The properties we need to know for structural design are strength, as in how much weight can we put on it before it breaks, density, as in how much room does it take per weight, and stiffness, as in how much does it bend under load. Great, so we just measure these properties? We kinda have to break the timber to measure them? Strength and stiffness, at least, can only be measured destructively, so you cannot measure them on timber that you still intend to use.
So how are we using timber in construction at all? Clearly there is a way to find out about these properties. People are using wood to build houses.
We sure can. We have to estimate the wood properties.
Estimate? Isn't that just a fancy word for guessing? You guess.
Yeah, we guess. Sort of. But we gather clues to make a well-informed guess, and we call that grading. Our clues are indicating properties that are related to strength, stiffness, and density. It's kinda like choosing a watermelon in the supermarket. You might look at it to decide if it's sweet. In wood, we look at features like knots, for example. Or you can take your watermelon and knock on it to decide if it's sweet by the sound. In wood, we use roughly the same technique to measure acoustic velocity. But most people don't really know what they are doing when they are knocking on their watermelon. But of course, we need to know how the indicating properties relate to the characteristic properties that we actually want to know. We need data from destructive and non-destructive testing to establish these relationships. And because wood properties vary so much, we need lots and lots of data. For some species, we would probably need to test all the wood we have. But someone did the work for the most common species and broke a lot of timber. We can grade conifers like Sitka spruce, and they are mostly graded to the strength class C16. Well, that's great news. So we do use this timber in construction? No, not a lot, no. Often architects and designers still perceive it as inferior and prefer to use higher strength classes like C24, and they mostly come from Europe.
That actually sounds like the safe thing to do. You are only guessing the wood properties after all.
Yes and no. The estimates we are making are mostly conservative anyway. And then there are additional safety factors used in the design. There is really no need to build in this extra safety layer. I don't know. It can't hurt, can it? Wood is cheap and plentiful. Wait, they're wasting all the wood I could use for my deck. Exactly. We actually do need to use our homegrown timber efficiently. Because guess what? The wood that we are burning for energy is probably good enough to be used for pretty much anything. We just need to do some research on wood properties and new grading strategies, especially for hardwoods. And we need to learn to value our homegrown timbers. Even for renewable materials like timber, we need to reduce, reuse, recycle. Wood waste can often be reused, even in structures if we manage to invent some grading procedures. And most of the wood that is demolition or construction waste, or even household waste, is probably still good enough to at least serve as fencing or packaging. I guess I could also build my deck from recovered timber. It might not look perfect in the end, but to be honest, whenever I start crafting things, they end up looking good enough, I guess.
Well, thanks very much, Marlene. Fascinating stuff. And it's slightly breathless tonight, as I say. We have a lot of speakers. So we now move on to Dr. Kamaljit Singh, who is an associate professor at Heriot University, who's going to talk about mounds of interest.
Hello, everyone. My name is Kamaljit Singh. I'm from Heriot University. So my presentation is about mounds of interest. So you might have seen big structures from 2 meter to 7 meter high on television or on real. So they are made by termites. And fascinating thing is that these termites are blind. So even though they're blind, they can make complex and very tall structures. So for decades, biologists were interested in studying these nests with the motivation. For example, this is a cartoon of the nest. If you measure the temperature outside these nests, it can fluctuate from 15 degree to 30 degrees centigrade day and night, depending on the country. But if we look into inside the nest, it's controlled within plus minus 2 or 3 degrees centigrade. So it's just because of the structure, the temperature is really well controlled. So the motivation here is that if we learn the mechanisms of temperature controls, so we can design energy efficient buildings. So the second thing, which is also interesting, so many people thought this is all blocked, nothing can pass through, but which doesn't make sense because termites, there are millions of termites living underneath. They need to exchange carbon dioxide they produce. So it has to go somewhere so that it can ventilate. So with these two motivations about learning temperature and ventilation controls, so we started exploring nests from Africa. So we brought 2 nests from Senegal and Guinea into our laboratories, and we imaged in 3 dimensions using a CT scanner, which is similar to what you find in a hospital. So what you see here, red is the solid, which is gray here, and the yellow is the internal structure, which is empty space where termites can move around. What our interest was looking into the microstructure, if it can allow the ventilation or the temperature controls. So with that motivation, we started making subsamples, even made like mini plugs, and we scanned them with the microtomography scanner, so which allows for a resolution of 1 micrometer. And this is what you see, an image from these machines in 2D, and this is an image in 3D. So black here is the empty space, which is filled with air. And the gray here is the solid ones, which you see in gray color here. In 3D, what you see blue is the empty space, which is black in 2D. So the first visualization, we can see there are 2 different types of empty spaces. We call them pores. They can be smaller pores or the larger pores. So we wanted to see how they are actually formed. We started looking into the videos. So what termites they do, they go around and put soil in their mouth, put saliva in, it makes a pellet, they compress it, the pellet could look like this. And the structure inside this pellet, compacted mass, could look like this here. But when the different pellets they put together, they can have empty space in between. It's just like a packing geometry problem. So what we were interested in looking into, although we were sure that this is not intentionally made, it's a packing geometry problem, but we wanted to know if there's any benefit of these termite, so these holes or empty spaces to termite nests. So another fascinating thing that we found, these holes, the larger holes, they were connected throughout the wall from outer to inside. So with this, we started doing lots of different simulations, computer simulations. And what it turned out to be, if there's a wind flowing outside this nest, So these large pores, they help to ventilate the nest very effectively. But let's say if there's no wind flowing, so we started doing more simulations, and it turned out to be the diffusion can kick in, and it can allow ventilation, passive ventilation of the nest, which is good for the nest. And second thing, which as you can assume, this is empty space and is filled with air, it can work as an insulator. So this can help to control to some degree the temperature or the thermal controls. Another thing, during this study, we found, let's say if it rains on the top of the nest structures, these are hydrophilic structures, means water likes to go into these smaller structures or the pore space. So when we did lots of different experiments, it turned out that the water can be soaked into the smaller pores. The larger pores, they stay empty because we need high pressure to invade these pores by water, which is not created by the rain itself, which is good because as soon as the rain stops, these larger pores can offer ventilation to the nest. So far we've done this study with thermoregulation, so the temperature or the ventilation, or to with the rain conditions. But our idea is to do further studies by combining simulations from small scale to larger scale to know the mechanisms, because once we know the mechanisms, so we can design energy efficient buildings. So in summary, I would say the 3D imaging, what we generally use for other fields, can help us to investigate the interiors of the termite nest. The key message here is that, again, if we know how the structure of these termite nests allow us to control the temperature and ventilation conditions, so we can design energy efficient buildings. So we don't need to design very similar to what termites, how they look like termite nests, but again, learning from the design and applying the physics to design new sort of modern buildings. With this, I'd like to thank for your attention, and I'd like to acknowledge lots of people who have contributed to this research field.
Well, thanks very much, Dr. Singh, indeed. So now we move on to Dr. Katherine Dunn, who is a lecturer in mechanical engineering at the University of Edinburgh. And now, this is quite the title, and I shall try read it slowly. Dr. Dunn will talk about electrosymbiotics. No, I got that wrong. Electrosymbiotics, a revolutionary new approach for net zero electricity generation and storage. So, Dr. Dunn, over to you.
Hi, I'm Dr. Katherine Dunn, and I'm a scientist and engineer at the University of Edinburgh. I believe that taking inspiration from nature can help us to develop technologies to solve the most pressing problems of our time, including the generation and storage of electricity without the release of carbon dioxide, CO2. I invented the new word electrosymbiotics to describe the creation of synthetic devices that use components derived from or inspired by biology to generate and store electricity. In the next few minutes, I intend to give you a flavour of what electrosymbiotics is and why you should care about it. The human race is pumping carbon dioxide into Earth's atmosphere at a rate of over 30 billion tonnes per annum. Carbon dioxide and other greenhouse gases are trapping extra heat and causing average global temperatures to increase. This is leading to significant climate changes with potentially catastrophic effects. For instance, we are experiencing severe weather events more often. Droughts, fires and floods are becoming more common, and the impact is devastating. Lives and property are already being lost, and the scale of the problem is only going to increase unless we dramatically modify how we do things. Carbon dioxide and other greenhouse gases are released from many different sources, including generating electricity and heat, industrial activity, agriculture and transport. We need to decarbonise in all areas, which means reducing the amount of CO2 we emit and potentially removing CO2 directly from the air. Generating electricity and heat accounts for a substantial proportion of global greenhouse gas emissions. We therefore need to implement new ways of generating electricity for homes and cities, eliminating sources that release CO2, such as coal, oil and gas. One zero-carbon energy resource is, of course, solar power. These days, it is more and more common to see solar panels on roofs and in fields, and a variety of solar power technologies exist. Obviously, the amount of sunlight we get varies dramatically from one location to another. Here in Scotland, of course, we don't get much sunlight, and it might seem more logical to use rain as a power source, if we could. However, we can potentially still extract a meaningful amount of energy from sunlight, even in Scotland, if we're careful, although obviously not as much as you could get from the equivalent solar panels somewhere like California or the Mediterranean. This is a rough sketch of the amount of sunlight that we get in Edinburgh throughout the year, from June through December through to the next June. This graph basically shows what everyone already knows, that sunlight is more abundant in summer than winter. This statement of the patently obvious reveals one of the big problems with solar power. It can't be relied upon to generate electricity exactly when you want it. If you want to use solar power to provide the electricity to make dinner after dark or to run an electric heater in winter, you might be out of luck. This means that we need to couple solar panels to energy storage systems such as battery banks. Conventional systems such as silicon photovoltaics and lithium-ion batteries do have major disadvantages. Manufacturing can be difficult and performance is limited. It is also tricky to recycle or dispose of them when they have reached the end of their lives. So maybe it's time we started looking for an alternative approach. We should look at the world around us and take inspiration from nature, which has had millions of years to evolve some very good solutions to a wide range of challenges. This is where electrosynbionics comes in. We can build devices that generate electricity and store energy by mimicking living things, or components thereof. We can even extract biomolecules and use them directly. Inspiration can be found in many organisms, including green plants, which perform photosynthesis to harvest sunlight, so they can use its energy to keep themselves alive. Green plants are not the only organisms that harvest sunlight. One species of microorganism uses something called bacteriorhodopsin, which uses light energy to move charged particles known as ions across a membrane to create a voltage. Bacteriorhodopsin and components from photosynthetic organisms can be used to make biological solar cells, an example of electrosynbionics in action. In fact, electrical effects underpin many key processes in living things, not just those involving sunlight. For example, our ability to actuate our muscles and sense the world around us depends on electrical signals in our bodies, based on mechanisms similar to those used by electric eels to stun their prey. All of these phenomena can provide inspiration for new devices. Some bacteria, which look a little like the microbes shown in this picture, release electrons into their surroundings. This stream of electrons constitutes an electric current which can be harvested and used in a device known as a microbial fuel cell. We can also make enzymatic fuel cells, where electric current is generated by a simple chemical reaction. Here, a biological molecule known as an enzyme triggers a reaction in which a raw material is broken down to form a product, and electrons are released to provide a current. Microbial fuel cells, enzymatic fuel cells, and other biological batteries that we don't have time to discuss are all examples of electrosynbionics. In the future, electrosynbionic devices might be able to power our homes and cities. Such devices are currently at an early stage of development, and great advances are needed to achieve the necessary performance. However, my analysis suggests that this will indeed be possible. Obviously, it will require extensive research and development involving a great deal of painstaking laboratory work. I am actively working on this, and my goal is to develop electrosynbionic technologies that will harvest sunlight, store energy until needed, and deliver electricity on demand, with zero CO2 emissions. I aim to deliver systems that are easy to make and recycle, which will compete on price and performance with conventional solar cells and batteries. Thank you very much for listening, and if you're interested, please follow me on Twitter or check out my website, both of which you can see on the slide at the moment. Thank you very much.
Indeed, thank you very much. Something which, is just vitally important as we move forward. So next we have Lewis, who is a PhD student at Glasgow Caledonian University. So Lewis's presentation title is The Energy Efficient Home, Clean, and affordable.
Just imagine yourself living in a planet that is so serene and completely green. To behold the lovely vegetation where you can feel and experience the very best nature offers. It will be so beautiful to see the mountains, the colorful skies, and the stable climate where our natural species are preserved, conserved, and not forcefully displaced from their native habitats. A planet where the birds, animals, fishes, and other creatures freely maintain the course and components of the ecosystem. It will be the paradise we all seek. But what do we see? A fast deteriorating planet, a world plagued with sorrows, pains, and hardship. We face the great hurricanes, the tornadoes, the awful floods, the tsunamis, the harsh storms, the sudden wild bushfires and droughts. Our world is no longer a safe place. We now must fight a lot of complications like climate change, global warming, and the COVID-19 pandemic. These are man-made death traps, as they are the byproducts of man's continuous excessive exploration and industrialization activities through the massive breakthroughs in science and technology. Consequently, we are faced with untold sufferings, terminal diseases, chronic sicknesses, extreme poverty, irreparable damage of properties, and countless loss of lives across both the developing and the developed countries. People have taken to the streets to demand for livable environment from the political class in leadership positions. People need government to tackle the elements of climate change, which are the actual causes of all the disasters troubling our present magnificent world. Let the protests on climate change continue, as we do not have a planet B. Global warming and climate change mean the same thing, and it is caused by changes in the Earth's greenhouse gases. Greenhouse gases like water vapor, carbon dioxide, methane, and nitrous oxide, in their correct composition, keep the Earth warm. Alteration to the natural composition of the greenhouse gases will affect the Earth's energy balance. Man's industrialization activities result in the emission of large quantity of carbon dioxide into the atmosphere. Increase in the percentage of carbon increases the amount of greenhouse gases and hence creating a climate change effect. Fuels that produce carbon or increase the amount of greenhouse gases are called fossil fuels. Example includes crude oil, petroleum gas, and coal. These are hazards to our lives and our environment. We need to stop the use of fossil fuels and go for clean energy alternatives that do not release greenhouse gases. Carbon is the main contributor of the greenhouse gases and very common in our everyday activities. Most of the energy we consume produce carbon. Now that we know the danger of carbon emission, we must deliberately cut down the use of carbon to the barest minimum. This will surprise you. Do you know that our buildings consume about 40% of the global energy demand and generate close to 24% greenhouse gases? The UK government is already embarking on net zero carbon energy projects to minimize carbon emission from buildings through the utilization of clean energy. This will be the subject of my discussion. I will be discussing the concepts of energy efficient homes with focus on how to make it clean and affordable. This is what my PhD research aims to achieve, and the knowledge contribution is to tackle global climate crisis. Clean energy refers to renewable energy resources from solar, wind, hydro, and so on. Kerosene is non-renewable. Renewable energy is non-pollutant. It's free in nature, sustainable, abundant, clean, and affordable. Solar is the most promising, prominent, and the cheapest form of renewable energy. Solar and wind power generators are very common in our societies today as an attempt to combating global warming. Solar energy towers and wind energy farms are constructed to power small towns, villages, and cities without any emissions of carbon. We now have commercial solar panels installed on the rooftops and facades. but the initial cost of installation of these silicon solar panels is very high. Hence, the indigent population continue to consume fossil fuels as they cannot afford solar panels. This is where my research comes in. I am proposing a less expensive solar panel that could replace the integral parts of the building structure, like the roof. My design will use efficient solar concentrators in place of the costly solar panels. My solar concentrators will be manufactured from cheap plastic or glass materials. My solar concentrator device has a wide hexagonal entrance that could enhance high packaging efficiency, increase performance by minimizing solar losses, and amplify the daily hours of electricity generation. When large amount of sunlight is captured by the solar concentrator, it is reflected through a small square exit aperture where a solar cell is attached. The solar cell then converts the sun energy into clean and useful electricity. When several of these solar concentrators are connected, they form an affordable solar panel that could be integrated into the building structure, which could generate all the electric energy required to power the home appliances, thus making the building energy efficient. For energy efficient homes, cost of solar panels will be significantly reduced. Cost of building materials will also reduce. Net carbon emission to the environment will become zero. Climate change will be mitigated, and our planet is recovered and safe. Thank you.
Well, Lewis, thanks very much for that. The energy efficient home, clean and affordable. That's exactly what we're looking for. Yeah. So moving on. Thanks very much, Lewis. Moving on now to Dr. Sarah Anderson and Dr. Shane Horgan. Sarah and Shane are both from Napier University, and their PechaKucha title tonight is Journeys Through Hacking: How People Become Hackers, Why They Stay, and Why They Quit. So, Sarah and Shane, over to you.
This is a brief tale about the beginning of a very long research road. It's about hackers, it's about crime and not. And it's about our attempt to research things a little differently. It's also an attempt to share with you why it's worth doing, or maybe even taking part in.
The project started in a pub, our most creative work environment. Shane is interested in all things cybercrime related, and me, Sarah, I'd been researching people's journeys away from involvement in criminal offending. There's a lot of research on desistance, as it's known, but so far mostly with people involved in offending in real life.
We wondered if existing theories of desistance would stand up in a totally different context, like illegal forms of hacking. One leading theory suggests that turning points in someone's life, such as getting a job or getting married, help explain why people stop offending, in part because they're just too busy doing other things in other places.
Of course, people with IT skills might be sat at their computer at work, so potentially they'd still have the opportunity to keep doing what they were doing. So this doesn't quite line up with what we know about conventional kinds of crime and why people stop.
Another theory focuses on shifts in people's identity, where someone starts to see themselves as a law-abiding person committed to pro-social values. But from what we knew, many people involved in hacking already have values that could be regarded as pro-social, even if they're not always pro-corporate.
This got us thinking. It got us thinking about the extent to which moves away from legal forms of hacking involve submitting to dominant values, neoliberal, political, ideological. And of course, whether that's what desistance means more generally, even for other forms of crime.
Since then, we've been developing this project. But even basic things have proved difficult. We keep coming back to one pretty crucial question. What are we even talking about? This is because each of the terms in our research question, desistance, illegal, hacking, are problematic in their own way.
The term hacking covers a wide range of different activities and crafts. Some, but not all, are highly skilled. Some have been pretty critical to the development of the internet, its security, and our privacy more generally. We added the term illegal in front to show that it is forms of hacking that are, or at least can be criminalised, that we're interested in.
but legislation and legality relies on tenuous definitions. Many people working towards improving cybersecurity engage in practices that law might deem illegal, such as independent security researchers exploring and cataloguing malware. So what might be deemed criminal in one context might be legal, encouraged, or condoned in another.
Meanwhile, state-led hacking practices that involve the hoarding of zero-day vulnerabilities operate with pseudo-legality. This is despite presenting a substantial risk to our collective security. Overall, when subjected to more careful scrutiny, legal and illegal are tenuous terms that weren't actually very helpful.
The term desistance then presents even more problems. There, literature is full of debate about how you determine whether someone has actually desisted from crime. When is it just downtime between offences? How do we know if someone has really stopped? One rather pessimistic perspective is that you're only fully evidenced desistance when you're dead.
Combining desistance with hacking only presents even more headaches. The diverse range of practices covered, the importance of context and on whose behalf you are doing them, and how these practices and contexts are interpreted by the prosecution and government means it's pretty hard to pin down where crime begins and where it ends.
Research so far has generally dealt inadequately with these definitional challenges. It's also offered explanations based on rational choice. The idea that people weigh up pros and cons, benefits and risks and decide. But this tells us little about how this subjective calculation is made, what thought processes and external events shape it.
Our approach aims to understand how people's pathways through hacking change over time, how it shifts from and between illegal and legal forms, passing through the many, many grey areas in between.
How does that address the definitional problems we mentioned earlier? Our plan is to circumvent it by being led by the definitions and meanings our participants ascribe to themselves, their work and activity. That's not to say those other formal definitions don't matter, but by approaching it this way, it'll help us unpack in evidence why legal definitions are problematic and need to change.
We want to understand how these journeys through hacking fit with people's online relationships, events in people's lives away from the computer, and the role of shifts in meaning, shifts in values, and shifts in how people see themselves within this. We're going to do this by gathering people's life stories.
The ethics and practice of this have been pretty challenging for us in our universities, given the sensitivities of the project and its data, and the fact that the criminal stereotype of hacker, rightly or wrongly, rings alarm bells with lots of different university departments. We've worked hard to put measures in place to protect us and our participants, but that's another much, much longer story.
So our plan was to go to international hacker and cybersecurity conferences and build connections there. And we'd persuaded the lovely people at Carnegie Trust in Scotland to pay for flights to Vegas to attend DEF CON, the biggest hacker conference of them all. But you all know what happened next. Cue COVID.
We've had to change direction and try to recruit people remotely through online forums. This has been really tough. But we brought on board another researcher, Ben, whose work on Tor and the values of Tor communities we both really admire and value. We want to get the message out to people who might have a story to share with us. So if you happen to know anyone, tell them to look us up.
For now, we leave you in suspense. We hope to come back next year and share our findings. We believe this work is important, that understanding how to stop harmful hacking practices while not constraining those trying to make us a little bit safer is a worthwhile pursuit. We hope this project can contribute to this aim, and until then, follow progress on our blog.
Well, thanks very much. And our final speakers tonight are Beth Trodden and Fergus Mcilwaine, both of whom are PhD students at Heriot Research Centre for Carbon Solutions. And their presentation title is The Search for Climate Change Solutions.
This year was really hot, but it was also really cold. And if you felt that it was maybe hotter or cooler this year compared to last year, you'd be correct. Extreme weather events, as well as extreme temperatures, were observed this year. And it may be that climate change is the reason and cause for this. All joking aside, climate change is impacting people's lives all over the world. It's destroying businesses, it's destroying homes, and it's posing a real hazard to human health and existence. This picture is from the UK just this year, and scientists say it's only going to get worse if we don't do anything about it now. Some of us may have heard about emission reduction goals such as reaching net zero by 2050. And if not that, maybe more of you have heard about Greta Thunberg on the news. And the point really can't be made clearer. We need to reduce our emissions and live sustainably. Right now, we need to reduce the amount of carbon dioxide in the atmosphere.
There's currently tons of CO2 in the atmosphere. Just to give you an idea of how much we emit, on the left is a white dot, which represents the trillions of stars in the universe. And on the right, that great big ball represents the CO2 molecules released every day. So what can be done? Our number one priority is to reduce the amount of carbon dioxide we release into the atmosphere. We can do this by reducing our dependency on fossil fuels, by using renewable power. In the UK, we normally use wind power, but elsewhere, solar and geothermal energy are used. We, as individuals, also have a part to play. And there are many things we can do, such as reducing consumption, cycling to work, and eating less meat. But with the scale of the problem being as large as it is, individuals can only do so much at home. Is there anything else we can do to help fight climate change?
I'm glad you asked, Beth. One thing that we can do is to capture the carbon dioxide at its source. This is where carbon dioxide is in its highest concentrations. And we can use carefully designed materials that act a little bit like sponges, which catch the carbon dioxide. Once we've captured the carbon dioxide, we need to work out a way to transport it to where it needs to go. This can be done using pipes, big trucks, or ships, just like the ones in this image. The important question to answer here is, how do we measure the amount of carbon dioxide that we're transporting? Because we're going to be transporting a lot through these transportation networks. I'm sure many of us have had to hunt for the gas meter at home when it's time to take the readings. The ones used to measure carbon dioxide are not much different. One of the things we need is a way to validate the existing meters to make sure that they're accurate enough to do the job.
So we have captured and transported the CO2. Now what do we do with it? Well, one exciting thing we can do is to use our chemistry skills. Using carbon dioxide and lots of chemistry, we can make useful products such as plastics, building materials like concrete, or fuels for cars. You might be thinking, wait, we're making fuels for cars? Isn't that the problem we're trying to solve? And you'd be right. But by using this fuel instead of a newly dug up fossil fuel, we create a circular economy, a little like the water cycle, where nothing new is added or taken away. We can also store carbon dioxide in underground rocks. You can see in this picture that we pump CO2 into deep reservoirs, where it is trapped. We take these funny looking samples from the rocks that look a bit like Pringle cans and study them in labs.
And the main question that we're trying to answer here is, will the carbon dioxide stay trapped? Researchers use imaging techniques to look really closely at the rock structure to answer this question. By studying the rock, we can work out how carbon dioxide interacts with it. We can also increase the amount of carbon dioxide that these rocks store safely. Our atmosphere is a little bit like a bathtub. The open tap shows carbon dioxide emissions entering our atmosphere, filling it up just like it would a bath. Today we've talked about ways to close this tap, but we can never fully close it. At some point we're going to need to pull the plug, removing carbon dioxide emissions that are already in the atmosphere. And that's where negative emission technologies come in. These are technologies that simply remove carbon dioxide directly from the atmosphere, and they don't release them back again. And the idea here is that these technologies are carefully designed to remove more carbon dioxide than they emit.
There are several proposed negative emission technologies. We can use trees, the ocean rocks and minerals, as well as specialised machines that remove CO2 from the air. Each of these have their own pros and cons, and we need to consider energy, the space it takes, and the financial cost. Some of you might be wondering why it's so difficult to remove CO2 before it gets into the atmosphere. It's not as easy as capturing it in a big net. It's really difficult because carbon dioxide is so similar to all its surrounding molecules. We have to find very special materials that capture carbon dioxide, and only carbon dioxide. Finding these special materials is difficult because there's so many trillions of possibilities. We need to use supercomputers to go through the many options. Then we can test each material individually to work out which ones are best for capturing CO2. A greener future is in our grasp. These technologies that we talked about today have the ability to halt climate change and possibly even reverse it. We still have some research to do, but if we use these technologies, and we all do our bit at home, we have a real chance of tackling climate change.
And we just have to do it. This is a time-sensitive problem, and as we mentioned earlier, we're already experiencing the impact of climate change. We know what technologies we need to use, and we know what we can do individually to help. We just have to do it, and we have to do it now.
So thanks very much, Beth and Fergus, and indeed thank you very much to all of our speakers. That has been a fantastic range of PechaKuchas, all very entertaining, all very informative. And hopefully this has whet your appetite for more. As I say, go to www.explorathon.co.uk and you can find out more of the events that we're doing across Scotland. And hopefully we'll see you at our third PechaKucha, which is next Wednesday night, and that's on science and technology. So thanks very much, everyone. Bye-bye.